In this video, we're going to look at how we integrate fractions, and specifically how do we decide which method we're actually going to use. So I'm going to go through a number of different scenarios that will hopefully cover most of the potential questions you could get asked. So you can read the first scenario here. Okay, it's where we have a fraction and there's only one term in the denominator. You see here we've got 2x squared. It's not 2x squared plus something else. Okay, we've just got one single term in that denominator. Now, something quite convenient to do in this scenario is to split this fraction up, in this case into three separate fractions, because we have three terms in our numerator. Okay, so what I could do, I could rewrite this as 5x cubed over 2x squared. And then it's going to be subtract, and it'll be 2x squared over 2x squared. So the denominator is always going to be the same. And then finally we got the plus 3, so plus, and then 3 over 2x squared, like that. And really, now we separated it. I should write it in brackets and then put the dx. Now, if you're confused as to how I've gone from here to here, think about it going in the opposite direction. Okay, because over here on the right, I've got three separate fractions with the same denominator. If that's the case, you should be able to add and subtract the numerators and write it as a single denominator. So essentially, I've just done the reverse of addition or subtraction. Now, what I'm going to do is I'm going to simplify each individual fraction using indices laws. Okay, so it would become 5 over 2. And then if we subtract our powers, it's going to become x to the power of 1. Like that. But the next fraction, the numerator and the denominators are the same, so therefore it's just going to become 1. And then for my final fraction, we haven't got x in the numerator, but when we integrate, we don't want x in the denominator. Okay, so we're going to have to rewrite it using indices laws again. And this time it's going to be plus 3 over 2. And to bring the x up to the numerator, we're going to have to make the power negative. So we'd have negative 2 like that. Now we've written every term in the form ax to the power of n. Now we can use the fact that when you integrate, you add 1 to the power and you divide by your new power. Okay, so let's go through and finish this off. Okay, so for the first one, it's going to become x squared. And then we're going to divide by 2 to get 5 over 4. Then the negative one is just going to become negative x. And then finally, for our final fraction, we've got x becoming to the power of negative 1. Common mistake is to go for negative 3. If you add 1, you're going to get negative 1. And then we're going to divide by negative 1, which just changes the sign. And then don't forget your plus c. Now let's have a look at our next scenario. You can see a description of the scenario there, but I'm going to talk through it in the context of the question and actually go through why we can't use the previous method on this one or why it's maybe not the best idea. So for the first strategy we looked at when the denominator only had one term. This time we have a 2x and a negative 3. Okay, and also the numerator is only a single term, so therefore splitting it into multiple fractions isn't really a viable strategy for this. Okay, so we're going to have to consider something else. Now, what we're going to consider here is the fact that when you integrate a fraction, where if we call the denominator f of x, and the numerator is the derivative of the denominator, then our integral is going to be of the form natural logarithm of the modulus of the denominator, and then, of course, our plus c. Okay, so we're looking for scenarios where the numerator is the derivative of the denominator, or a numerical multiple of it. And in terms of what types of fractions where this might occur, you see how the denominator, I mean, it's not written in brackets, but if I did, the power here would be 1. Okay, the fact that the power there would be 1 is indicating to me that maybe I'm going to have to use the natural logarithm, okay, for this type of question. Because remember, if we have x to the power of negative 1, which is what I'd get if I sort of rewrote it with indices laws, remember we can't integrate that by adding 1 to the power, because that's going to be 0 and we can't divide by 0. Okay, so in these scenarios, it's quite common to use the natural logarithm. Now, to check whether the numerator is the derivative of the denominator or a numerical multiple of it, I need to go to my denominator and I need to differentiate it. So if we differentiate 2x take 3, I'm going to get 2. Then the question is, in order to get from 2 to our numerator of 5, do we have to multiply by a numerical value? So nothing involving x. And the question is, yes, we can. Okay, you'd have to multiply by, and we can go via 1. If you do 2 divided by 2, that gets us to 1. Okay, and then times by 5 gets us to 5. So in terms of the direct route, we're dividing by 2, that goes in the denominator, and then we're multiplying by 5, that goes in the numerator. So then we can write out our answer. Okay, so it's going to be ln, a natural logarithm of the modulus of the 2x subtract 3, which is the denominator, and then we're going to have to put the 5 over 2 in front, like that. And then it's going to be plus c. Now let's have a look at our next scenario. So let's rule out our first two possible strategies. So do we have one term in the denominator? Well, within the brackets, we have the 2x subtract 3. So I'm not going to go through that method of splitting up the fraction. Okay, I don't think it's going to really work. Now let's consider the natural logarithm. Now that's usually for when the denominator is raised to the power of 1. As you can see, we now have a squared around the bracket in the denominator, so therefore we're not going to use the natural logarithm. In this scenario where the power is something other than 1, what you're going to want to do is rewrite the fraction using indices laws. So we'd have 5, and to bring the denominator up to the top, we would write 2x subtract 3, but it's going to be to the power of negative 2 instead. Okay. Now, once we've done this, we have to consider whether we can use the reverse chain rule or use integration by parts. So let's do a check for the reverse chain rule. The check for that is to differentiate your brackets. So if I differentiate 2x take 3, that's going to give me 2. And then ask yourselves, in order to get from 2 to what is multiplying the bracket, do you have to multiply by a numerical value? Well, we already discussed this in the previous example. Yes, you would. Okay, so therefore we can use the reverse chain rule for this one here. Okay, so that's what we're now going to carry out. So when we do our reverse chain rule, our bracket stays the same. We add 1 to the power. Okay, so that's going to give us negative 1. And then that 5 that was in front, okay, we are going to divide it by our new power negative 1. And then also by the derivative of the bracket. So the derivative of the bracket is the 2 here. Okay, so I'm going to times by 2 in the denominator to indicate we're also dividing by 2. Then we can write out our final correct answer. So let's just put the plus c in. Okay, so if we simplify, we get negative 5 over 2. And then it's 2x subtract 3. Power of negative 1 plus c like that. Now you could write it back as a fraction, but it doesn't really matter. Okay, let's have a look at our next question then. Okay, this one here. So once again, let's go through our possible strategies. So is there one term in the denominator? Well, no. Okay, is the denominator raised to the power of 1? No, it's raised to the power of 2. Okay, so we're going to use indices laws to rewrite this. So we'd have 5x, and then we'd have 2x subtract 3 to the power of negative 2 with respect to x. Once we've done that, we have to now ask ourselves, can we use the reverse chain rule? So if we differentiate what is in our bracket, okay, which we've done previously, the 2x take 3, we get 2. Now, in order to get from 2 to 5x, which is what's multiplying the bracket, do we have to multiply by a numerical value? The answer is no. Okay, you'd have to multiply by something involving x. Therefore, we cannot use the reverse chain rule for this question. Instead, we're now going to have to try and do integration by parts, because essentially we've got ourselves a product, so it's a viable option. So integration by parts, you need to start by selecting your u, which you're going to differentiate, and your dv by dx, okay, which you're going to integrate. Now for the u, remember the priorities are, first, anything involving natural logarithm, which doesn't apply here. The number 2 is any polynomial term, so anything of the form ax to the power of n. So in our product, we have 5x, and we have our brackets here to the power of negative 2. Well, the 5x is of the form ax to the power of n. Okay, so that is going to be my u. And then therefore the rest of the expression we're integrating is going to have to be our v dash. Then what we're going to have to do next is differentiate my u. So that gives me 5, which is nice to have a numerical value. And then we're going to have to integrate our v dash. Okay, so let's check. We have a bracket raised to a power. Can we use the reverse chain rule? Well, when we differentiate 2x subtract 3, I get 2. In front of the bracket, we got a 1. To get from 2 to 1, do we have to multiply by a numerical value? Yes, so we can use the reverse chain rule in this case. Okay, what is going to happen is we're going to have our bracket, but we're going to add 1 to the power to get negative 1. Okay, and then we're going to take what was initially in front of the bracket, which is 1, and we're going to divide by new power negative 1, and also by the derivative of what's inside the bracket, which is the 2, like that. Okay, so then let's go through and just simplify that. We negative a half times 2x take 3 to the power of negative 1. So now we can use the integration by parts formula. I'm just going to make a little bit of space here. Okay, so then we can say that our integral here is equal to, and it's going to be u times v. Okay, so v is here. So it'll be 5x times this fairly complicated looking expression. So we would get negative 5x over 2 and then times 2x take 3 to the negative 1. Subtract the integral of the two things that we had to find ourselves. So in my layout, that's going to be the bottom row. Okay, so that's going to be the 5 multiplied by the negative half, 2x take 3 to the negative 1. Okay, so when I multiply those, I'm going to get negative 5 over 2, and then 2x take 3 to the power of negative 1 with respect to x. Okay, so what I'm going to do next, just to make life a bit easier, is this numerical factor in the integral, I'm actually going to pull that out. Okay, so what we would get then is what we've already integrated here. Okay, and then it's going to be a plus, because we've got a negative and a negative, and then 5 over 2, and then the integral is going to be of 2x subtract 3 to the power of negative 1 with respect to x. Okay, so now we're going to have to do this next integral. Now, we've already got it in a set way where we've got it written in terms of an indice without it in the denominator, but the issue is this power of negative 1 means I'm not going to be able to make use of the approach of adding 1 to the power, because the power is going to become 0. But actually what I'm going to do is just rewrite this integral again as a fraction, just to help visualize things. Okay, so once I've done that, I would get 1 over 2x subtract 3. And then let's go for our strategies for fractions. So is there one term in the denominator? No. Okay, is the denominator raised to the power of 1? Yes, it is. Okay, so let's check if we can use the natural logarithm. If you differentiate 2x subtract 3, you get 2. Okay, to get from 2 to 1, our numerator, do you need to multiply by a numerical value? Yes, you need to multiply by a half. So therefore, we can use the natural logarithm. It's going to be what we've already got here. And then we would have plus 5 over 2. And then from my integral, I am going to have ln of the modulus of 2x subtract 3. Again, I'm going to multiply by a half. And then I will close this bracket, and then we've got plus c. So we pretty much got our final answer here. Okay, the one thing we can go and do is we can multiply the 5 over 2 by a half to get 5 over 4 ln of the modulus of 2x subtract 3. Let's take a look at our next scenario. Okay, so this is our new scenario. Now you can see a written description above of what I'm going to talk through, but I'm going to talk through it via the example. Okay, so is there one term in the denominator? No, there are multiple terms, so probably splitting up the fraction isn't going to be the best approach, even if there are multiple terms in the numerator. Now, is the denominator raised to the power of 1? Yes, it is. So let's consider natural logarithm. If I differentiate the 3x take 2, okay, I get 3. Now, in order to get from 3 to our numerator, 5x take 4, can we multiply by a numerical value? Well, no, because we'd have to introduce x. Okay, that's not going to work. So therefore, we're not going to use the natural logarithm. Now, our next potential choice is, could we use indices laws? Well, the denominator is raised to the power of 1, so no, we don't want a negative 1 power when we bring it up to the numerator. Okay, so we're going to need a new strategy. Now, this fraction is an example of improper fraction. The reason is, if you look in the numerator, okay, we have a polynomial in x, okay, we're only considering whole number powers here. We wouldn't be considering this for fractional powers. Okay, the highest power of x is 1. Now, in the denominator, the highest power of x is also 1. In this scenario, where the highest power in the numerator is the same as or greater than the highest power in the denominator, you've got an improper fraction, and we're going to use algebraic division to rewrite the fraction. Okay, so I'm going to take this off because I'm not interested in this, and I'm going to set up an algebraic division. So under our division, we got 5x subtract 4, and then outside we've got 3x take 2, which is our divisor. So we're going to do 5x divided by 3x. Okay, so I'll just write the calculation here. So the x's cancel, so we're left with 5 over 3, which is a numerical value. It's a constant, so I'm going to put it in this column over here. Then we take that 5 over 3, and we multiply by 3x. Now, if we do that, we should end up with 5x again, which I'm going to write here. And then we're going to take that 5 over 3 and multiply by negative 2. So we're going to get negative 10 over 3, like that. What we then need to do is calculate the remainder. So we're going to do a subtraction. Now, the 5x's will cancel. And then we're going to do negative 4 subtract negative 10 over 3. So we're going to end up adding. And that is going to give me negative 2/3. Now that we've done that, what we're trying to potentially do next is do negative 2/3 divided by 3x. However, the power of x in the 3x is greater than the negative 2/3. So we're actually finished there. But negative 2/3, that is our remainder. And now we can go and rewrite our integral. Okay, our integral, our fraction, we're only rewriting the fraction, we haven't done the integration yet. Okay, it's going to be the integral of our quotient, which is the 5 over 3. Okay, and then it's going to be plus our remainder. Now, our remainder is negative, so I'm going to write negative, and then our remainder, which is 2/3. And the idea is your remainder has not actually been divided by 3x take 2 because we couldn't fit 3x take 2 into it. So therefore, I'm going to write 3x take 2 here like that. And then in brackets, dx, because we got multiple terms. So now let's try and integrate what we've got there. So let's integrate my first term, which is just a constant. So that's just going to become 5/3 of x. Okay. And then that fraction's looking a bit more complicated. So I'm just going to write it again over here. We've got to subtract. And then we'll have the integral of 2/3 over 3x take 2 with respect to x. Now, just to make life easier, this numerator looks a bit complicated, so I'm going to factor that out. So we got 5/3 of x, subtract, and then we'd have 2/3, and then the integral of 1 over 3x take 2, which looks a bit nicer. So now we've got another fraction to integrate, so we're going to have to go through our possible methods. Hopefully, you may be getting a bit quicker spotting which method you're going to do. Okay, because we've got multiple terms in the denominator, so we're not going to split the fraction up. Now, the denominator is raised to the power of 1. If I differentiate that denominator to consider the natural logarithm, we would get 3. Now, to get from 3 to 1, would we have to multiply by a numerical value? Yes, we can multiply by a third. Okay, so therefore, the integral would be 1/3 of the natural logarithm of the modulus of 3x subtract 2. Okay, close bracket, and then we'd have plus c like that. Okay, and then the last thing we can do is multiply by the 2/3 outside the bracket to get negative 2/9, and then the rest of our expression. Okay, let's have a look at another question then. Okay, so we got this fraction here. Now let's go through our potential strategy. So in the denominator, we got multiple terms, so we're not splitting up the fraction. Now let's consider natural logarithm. If I differentiate 3, take 2x, I'd get -2. To get from -2 to 5x squared, you'd clearly have to multiply by something involving x. So we're not going to use the natural logarithm, at least not yet. Okay, indice laws. Well, denominator is to the power of 1, so we're not going to want to write it as a power of -1. Okay, and as you'll see, we actually have another improper fraction, because the highest power in the numerator is 2, the highest power in the denominator is 1. Okay, so in this scenario, we're going to do algebraic division again. So let's set it up. We'd have 5x squared, okay, and then 3 subtract 2x, like that. Okay, so what we're going to do also is I'm just going to write in a plus 0x and plus 0. I like to just have that in so it's got the format of the decreasing powers. So then we're going to do 5x squared divided by -2x. So 5x squared over -2x, which would become -5 over 2, and x squared divided by x is just x. Okay, so I then write that in my x column, so -5 over 2x. Then we're going to take that and multiply by -2x, which should give you 5x squared again. Okay, if you've done things correctly. And then -5 over 2x times 3. So that would be negative, and then it's going to be 15 over 2x. Then we're going to subtract to get our remainder. The 5x squareds cancel, then 0 subtract -15 over 2x becomes positive 15 over 2x. Okay, and then what we have to do next is do the 15 over 2x divided by the -2x. Okay, so I'll write that calculation over here. 15 over 2x divided by -2x. Okay, the x's cancel, so we're left with -15 over 4. Okay, which I'm going to write over here. Now what we're going to do next is carry down our plus 0. Okay, and then we're going to do -15 over 4 multiplied by -2x. Okay, which should get me back to positive 15 over 2x if I've done things correctly. And -15 over 4 times 3 would give me -45 over 4. Then we're going to subtract to find our remainder. Okay, so that's going to give me the 15 over 2x's cancel, and then subtract -45 over 4 gives me positive 45 over 4. Okay, and now the power of the 45 over 4 is lower than the -2x, so we're finished with our division. So we can now rewrite our integral, so it's going to be the integral of, and it's going to be our quotient up here, so -5 over 2x subtract 15 over 4. And then our remainder, so plus, and then it's 45 over 4. And the idea is we haven't divided that by the 3 subtract 2x. So that's going to go up there. And then in brackets, dx. Now let's start doing the integration of each term. So the first two terms are fairly straightforward, okay, because they're of the form ax to the power of n. So we increase the power by 1 to get x squared, divide by 2 to get -5 over 4. And then for our next term is a constant term, so that's just going to become -15 over 4x. Now my last term looks a bit more complicated, so we got a plus. I'm going to factor out the 45 over 4. And then we still got to integrate the fraction left over, which is going to be 1 divided by 3 subtract 2x with respect to x. So let's have a go at integrating that fraction. And what you'll find is once you've done your algebraic division, you usually will end up with a fraction where you can use the natural logarithm. That's sort of some of the goal of this. So if you differentiate 3 subtract 2x, you get -2. To get from -2 to 1, we'd have to multiply by -1/2. Okay, so then we would get -1/2 ln of the modulus of 3 subtract 2x. Okay, and then close your bracket, and then plus c. Okay, and then you can expand the bracket with the 45 over 4 and the -1/2 if you want, but I'm going to stop there. So you can have a read of the new scenarios we're going to consider now, but I'm going to talk through it via some examples. So we've got our integral here. So let's go through our strategies so far. So does the denominator have only one term? Clearly not. It's got 3 terms, so we're not going to split fraction up. Okay. Then we'd consider our natural logarithm. Okay, so let's differentiate our denominator and see what we get. So if I differentiate x squared plus 7x plus 12, my answer is 2x plus 7. So if we have 2x plus 7, and I want to get to my numerator of x plus 3, do we have to multiply by a single numerical value? No. Okay, it's not possible to get from 2x plus 7 to x plus 3 by multiplying by a single numerical value. So we can rule out our natural logarithm. Now we'll consider whether we can use indices laws. Well, the denominator is to the power of 1, so we're not going to want to use indices laws to rewrite that. Okay, so we've ruled that out as well. Now, is it an improper fraction? Well, the highest power in the numerator is 1. The highest power in the denominator is 2. Therefore, we don't have an improper fraction because the power in the denominator is higher. Okay, so we're going to have to consider a potential new strategy, okay, which works quite effectively when you're polynomial in the numerator and in the denominator. So we've got linear expression in the numerator and the denominator has a quadratic. What we're going to do is we're going to factorize both the numerator and denominator and see if we can simplify. So the numerator x plus 3, there's nothing we can actually do with that. Okay, so let's consider our denominator and whether we can factorize that. And I believe we can. We get x plus 4 multiplied by x plus 3. But the next thing to consider is, can we simplify this fraction? Well, there's a common factor of x plus 3, so we can cancel that out. So it's going to become 1 over x plus 4 with respect to x. Now we've got a sort of a new fraction to consider. Of course, it has the same value as the original fraction, but it's a different way of writing it. So let's go through our strategies again. Do we have one term in the denominator? No. Okay. If we differentiate the denominator, so if we differentiate x plus 4, we get 1. Okay, and in order to get from 1 to 1, we'd multiply by numerical value, which is just 1. Okay, so therefore we can use our natural logarithm. It is going to be the natural logarithm of the modulus of x plus 4 plus c. Okay, and because it's multiplied by 1, I don't have to write anything in front. Okay, so that will be the answer to that question. And let's look at another one. So let's go through our strategies. So one term in the denominator, no. If we differentiate our denominator, we would get 2x take 3. And clearly we're not going to get to 2 by multiplying by a numerical value. So that's not going to work. Indices laws, well, the denominator is to the power of 1. So we're not going to want to use those. Is it an improper fraction? Well, there's a constant in the numerator, so it's not going to be. Whereas the denominator has a quadratic, so definitely not. Okay, so our next strategy is to factorize and see what happens. So 2, and then in our denominator, the common factor of x. So we'd have x and then x take 3, like that. Now, clearly we can't simplify this fraction any further. So the next thing we're going to try and do, given that we factorized our denominator, okay, we're going to try and do partial fractions. So you can do partial fractions when you have a quadratic or a cubic denominator, which you can factorize into at least 2 factors. Okay, so in this case, we're dealing with a quadratic one. So if I was going to do partial fractions, which I'll do a little bit lower, our setup for this would be that this is identical to a over x, which is one of our factors in the denominator, plus b over x plus 3, which is the other factor we have in the denominator here. Then what we're going to do next is go to that right-hand side, and we're going to try and write it under a common denominator. So we'd have our first fraction would multiply by x plus 3 over x plus 3. So we get a over x plus 3 divided by x times x plus 3. And then for our second fraction, we're just going to multiply by x over x. So we'd get bx over x times x plus 3. Now we'd be able to raise this fraction over a single denominator, okay, of x times x plus 3. And our numerator would be a times x plus 3 plus bx. And the idea is, given that the denominator here is the same as the denominator here, we can equate the numerators if this is going to be identical. So we can do 2 is equal to this expression here. So we'd have 2 is equal to a times x plus 3 plus bx. Then what we're going to do, we're going to pick a value for x that we're going to substitute into both sides, as we should get the same value on each side. So a convenient value to pick, given that we've just got x multiplying the b, I'm going to consider when x is equal to 0. So we would get 2 is identical to, and it would be, if we put 0 in for x, we're just going to get 3 in the bracket, so we'd have 3a, and then the bx, well, that would become 0 if x is 0. So therefore, we can obtain that a must be equal to 2/3. Now we're going to think of another value that we could potentially substitute in here. So given that this bracket here is x plus 3, I think if we substitute x equals -3 in, we're going to get a good result. Okay, so when x is equal to -3, we would get that 2 is identical to, and this bracket would be 0, so we get 0a, so we'd just be left with b times -3, which would be -3b. So therefore, b would be equal to -2/3, like that. So what I can now do is go back to my integral, and we're going to use both of those values. So I'd write equals to, and then our integral symbol, and then in brackets, because we're going to have multiple fractions added or subtracted together. And we've got a over x, so that would be 2/3 over x. And then we've got the negative for b, so I'm going to put the negative in front, and then we're going to put 2/3 in the numerator, and it's going to be x plus 3 in our denominator, and then close brackets dx. So what I'm going to do next, given that 2/3 is common to both numerators, I can factorize it out of the entire integral. So we get 2/3, then our integral symbol, and it will become 1 over x subtract 1 over x plus 3 with respect to x. And now we're in position to integrate. So we're going to have our 2/3, and then I'm going to put my result in brackets. Now 1 over x, this is the most basic scenario for the natural logarithm. That is natural logarithm of the modulus of x, like that. That should be one you should just be able to recognize. Now for our second fraction, we got multiple terms in the denominator, so we're not going to split it up. Now if we differentiate our denominator, we get 1. In order to get to 1 in our numerator, well, you'd have to multiply by 1 in numerical value. So we can use the natural logarithm again. We'd have our subtract, and then we'd do the natural logarithm, the modulus of x plus 3. And given that this value is 1, we don't have to write anything additional. So then we'd have this, and it would be plus c, like that. Now what we could potentially do further is you could use log laws here to potentially clean up what is inside the brackets. So inside the brackets, we could write that we would have the natural logarithm of our x, and it would be divided by, because it's subtract, and then we would get x plus 3, like that. And we'd still have our modulus symbols, and then we don't actually need our brackets anymore, so I'm just going to tidy that up. And then we've got our plus c. Now there is something we can do to get the plus c into our logarithm, okay, which is something you're often expected to do, especially when differential equations are involved. Okay, and what we can do is rewrite our c in a slightly more complicated way. Now this isn't particularly obvious to do, but the idea is the plus c is the most basic way of writing your constant, but you can write it in many other ways. Now another way we could write this constant is, what we could do is we could write plus, and then I'm going to write 2/3 ln a, like that. Okay, because if you're doing a as a constant, then the natural logarithm of a constant is also a constant, and 2/3 times the natural logarithm of a constant, okay, will also be a constant. So it's just a more complicated way of writing the plus c. Now the reason I've done it like this is because we've got 2/3 here and 2/3 there, so essentially we can factor that out. So we would have 2/3 And then in brackets, we would have the natural logarithm of the x over x plus 3, and then plus the natural logarithm of a, like that. And what we can do next, because we've got a plus here, we can now multiply our arguments of our natural logarithms together. So we could get a final cleaner answer of 2/3, and then the natural logarithm, and it would be ax over x plus 3, like that. Again, that's sort of the neatest way we could potentially give our answer. So let's have a look at our next scenario. So once again, you can have a read of the little description written there at the top, but I will talk through by the examples. Now we're going to be looking at fractions involving trigonometric functions, which always look a little bit more complicated. So I've got the formula booklet here, and the other thing we do have to consider is potentially using identities to write our fraction in a way that we can use one of the strategies we've already talked about. But let's go through and see if we can use some of our existing strategies before using identities. So have we got one term in the denominator? Well, yes, we have. So let's have a go at splitting up my fraction. So I'd get the integral of 1 over cos squared x, and then we'd have plus, and our denominator would be cos squared x again, because essentially we're doing the reverse of addition, and our numerator would be cos x. And that's with respect to x. Then let's try and simplify my fractions and see what we end up getting here. So for my first fraction, if we got 1 over cos squared x, okay, that could become sec squared x. And now we're making use of identities, okay, our reciprocal trig functions. And as you can see, if we got sec squared here, you can see it's in our formula book. So I like the look of that. Then for our other fraction, okay, we have a cos x divided by cos squared. Okay, so that would be cos x in brackets to the power of -1, which is essentially 1 over cos x, which is sec x. So we're going to get plus sec x, and then that would be with respect to x. And as you can see, sec x is also written here in our formula booklet. So it seems that we're in position to integrate. We shouldn't have to do any further identity work. So the sec squared x, when integrated, would give us tan x. And then when we integrate the sec x, if we look at this one, it's a little bit more complicated. We get the natural logarithm of the modulus of sec x plus tan x. And then, of course, we would have plus c. And that would be our final answer. Let's have a look at another question. Okay, another fraction involving trigonometric functions. So do we have one term in the denominator? No, we got a 1 plus cos x. Now let's consider our natural logarithm. So if I differentiate our denominator of 1 plus cos x, do I get a numerical multiple of our numerator? Well, if we differentiate 1, we get 0. If we differentiate cos x, we get negative sin x. So I've ended up with negative sin x. If I want to get to our numerator, which is 3 sin x, what do I have to multiply by? Is it a numerical value? Well, yes, it's going to be -3. Therefore, we can use our natural logarithm. So our final answer is going to be -3 lots of the natural logarithm of the modulus of our denominator, 1 plus cos x. And then don't forget your plus c. So we didn't even necessarily need to use the formula booklet that time or any identities. Right, next question. So let's go for our strategies. Is there one term in the denominator? Clearly not. Okay, natural logarithm. If we differentiate our denominator, well, it's going to involve trig functions. Clearly, it's not going to be a numerical multiple of 1. So we don't have to worry about that. I'm not actually going to write out the differentiation. Indice laws, well, the denominator is to the power of 1. So I don't like the idea with that. So before we go any further from there, because after that it's about improper fractions, which is related to when we have a polynomial in the numerator and denominator, which we don't have here because we've got trig functions. The same with the partial fractions. What I'm going to think about is, could I use identities to rewrite my denominator so I've only got one term? And yes, we can, because we can use the identity that is sine squared theta plus cos squared theta is identical to 1. So we can rewrite this integral as 1 over, and it's going to be, if we rearrange our identity, we'd have cos squared theta is identical to 1 take sine squared theta. So if we have 1 take sine squared 2x, that is going to become cos squared 2x with respect to x. Now we've got a single term in the denominator. Now we're not going to split fraction up because our numerator is just a single term. But can we write 1 over cos squared 2x in a different way? Well, we could write it as sec squared 2x with respect to x. And if we look at our formula booklet, we've already used this before in this video, we have sec squared there. So now we can integrate, and it's going to become 1 over 2. Okay, that's the 1 over k part, and it's related to the 2 in here. And then it would be tan, and then the angle always stays the same when integrating or differentiating with trig, and then plus c. So let's have a look at another scenario. So this one is pretty much our final scenario here, and it's the idea if all of the above fails, we are going to try an integration by substitution. Now, in terms of why all the above fails, well, one term in the denominator, clearly not. We got a 1 and a root x. Natural logarithm, well, if I differentiate my denominator, we've got a fractional power on the x because it's 1 plus x to the half. So once I differentiate that, I'm going to end up with a half x to the negative a half. Again, we've got x to the power of 1 in the numerator, so they're not numerical multiples of each other, so we don't have to worry about our natural logarithm. We're not going to use indice laws to rewrite this because the denominator is to the power of 1, and then we're not going to worry about our improper fractions or partial fractions because our denominator is not a quadratic or a polynomial or a cubic. Okay, it's got that root in it, so we're not going to do those processes. Therefore, I've sort of come to a point where none of my methods are working, so we're going to try a substitution. Now, in terms of what should the substitution be, well, usually it's something related to the denominator of a fraction. Let's say the denominator was something that looked a bit like this. Then our substitution might be what is in the bracket raised to a power, so we'd say u is equal to 2x take 3. Now, in this case, we don't have something raised to a power, so one option is just to make the entire denominator the substitution. So we could go with letting u equal to 1 plus root x. Now, your other alternative is to make u equal to something that's just quite complicated in the denominator. So we could go with just the root x. I believe both of these will work, but I'm going to do the first one that I wrote here instead. Now, integration by substitution, the first thing I would do is go and differentiate our substitution. Although I don't like the fact that this root x is going to be a fractional power, and if I can avoid that in my differentiation, I want to. So one thing you could do is rearrange our substitution to make x the subject instead. So we're going to have u subtract 1 is equal to root x, and then to get x on its own, we're going to square both sides. So we get u take 1 squared is equal to x. I'm now going to differentiate. So I would get dx by du because our x is our subject, and we're going to differentiate with respect to u. And then you could use the chain rule of differentiation on this side here. So we multiply by the power to get 2. We differentiate what's in the bracket, which is 1. So we're going to multiply by that as well. And then we'd have our bracket u take 1, but it would be raised to the power of 1 instead. So if I just simplify what I've ended up with there, I would have 2 lots of u take 1, like that. Now I need to replace dx here, so I'm going to make dx the subject, so dx would be equal to 2 lots of u take 1 du. Now let's start substituting into my integral. So I'm going to leave the x on the numerators. There's not much I can do with that yet, but my denominator is equal to u, as we set the denominator equal to u, so I can replace it with a u, which I like. And then the dx, I can replace that with my differentiation. So then I would write times 2u subtract 1, and then it would be du like that. Let's just simplify what's written here. So in my numerator, I've got x, and then we've got the 2, but I'm actually going to bring the 2 out to the front because it's a numerical factor, and then we'd have u subtract 1 over u du. Now, can I simplify in any way, okay, to potentially remove the x, because we don't want that in there when we integrate, because we're trying to do with respect to u? The answer is no, there's no way I can magically remove the x, so I have to head back to my substitution and make x the subject so I can replace it here. Now, fortunately, I've already done that. I made x the subject down here, so therefore I can replace x with the u take 1 squared. So I would get 2, and then my integral symbol, and it would be u take 1 squared multiplied by u take 1 over u with respect to u. Like that. So now my integral is entirely in u, so sort of the substitution aspect is complete, but I now have to integrate. So I'm just going to simplify that further first, because on the numerator I can write it as u take 1 cubed, and that's over u with respect to u. Now if we go through my strategies, our denominator is a single term. So we could try splitting the fraction up, but in order to do that, I first need to expand the brackets, which might take a little bit of time because it's cubed, but we can use our knowledge of the binomial expansion to help us. So I believe we would get u cubed, and then it would be negative 3u squared, then plus 3u, and then it would be negative 1, like that. And then it would be a u in the denominator, and then we'd have du. Now I'm in position to split this fraction up, and it's going to be 4 separate fractions because in the numerator we have 1, 2, 3, 4 separate terms. So to have 2, don't forget the 2, and then my 4 separate fractions would be u cubed over u, take away 3u squared over u, plus 3u over u, subtract 1 over u with respect to u. Then let's go through and simplify each fraction individually. So I would get u squared, and then it would be take away 3u, and then it would be plus 3, and then we've got negative u to the power of negative 1 if I don't want to write u in the numerator. However, I don't like the negative 1 power, so actually I'm going to leave it as 1 over u with respect to u. Now we can go through and actually integrate, so start writing out my answer. So add 1 to the power to get u cubed, and then divide by it to get a third. Then add 1 to the power to get u squared, divide by it to get 3 over 2. Then the plus 3 just becomes plus 3u. And then the 1 over u, well, that's our standard integral for the natural logarithm. That would just be negative natural logarithm of u, close bracket, and then plus c. Now, technically, you could write the plus c inside the brackets as well. It wouldn't matter. But that would be not my final answer, because despite all the hard work I've done, I still need to reverse my substitution, because this is in u, but my initial integral is in x. So I'll write our substitution back down here. It's u is equal to 1 plus root x. So what I'm going to go through and do is replace all of those u's with the 1 plus root x. So we'd have it cubed, then we'd have it squared, then we'd have it to the power of 1, and then we'd have the natural logarithm of it, and plus c. Now there's probably some factorizing that you could do involving these, but I'm just going to leave it there as I think that's a sufficient answer.